Hello everybody, this is the video solution guide to group work P2, which is about collisions. So question 1 gives us this scenario. It has two railroad cars. One is an empty railroad car with this mass, and it's going north. So I have made north be the positive direction. And then you have a second railroad car that's all loaded up, and it has this mass, and it's at rest. So that means that the velocity at the beginning is 0 meters per second. So when this car runs into this car, they stick together and produce this new coupled railroad mass that's like now a combination of both masses all together. So after these two have been run into each other, the final velocity is now 1.23 meters per second. And the time it takes for this railroad car, the first one, to go from its initial to its final is 2.25 seconds. So this is the explanation, that this is the amount of time the collision takes. So this is the question. Calculate the force that slows the empty car down. So force is equal to impulse divided by time, or mass times delta V divided by time. So here's the mass, and here's how much it changes its velocity by. So the force necessary to change the object, the empty railroad car, from a velocity of 4.92 meters per second to 1.23 meters per second is a leftward force, so a force to the left. So this number should be negative because the force is pushing it to the left. So the loaded car is pushing on the empty car, just like the empty car is pushing on the loaded car. So if you know nothing else about physics, hopefully you know these three laws from Newton. And the third law says that for every action force, there's an equal but opposite reaction force. So the force that slows the empty car down is negative 184,000 newtons. That's the same value of the force that causes the loaded car to speed up. So this loaded car has this mass, and it goes from an initial velocity of 0 to plus 1.23. That's why its delta V is positive. And it takes the same amount of time, delta t of 2.25 seconds. So if you do this math and this math, you get the same number. It's just that one is positive and one is negative. The reason they are equal is because Newton's third law says that for every action force, there's an equal but opposite reaction force. And if you think about the equation related to Newton's law, Newton's second law says that F equals ma. So if the forces are equal but the masses are smaller, that means it should have a higher acceleration. And vice versa. If you have a high mass and the same amount of force is applied, it will have a lower acceleration. So mass and acceleration, if force is constant, mass and acceleration are inversely proportional. That's what that means. All right, I accidentally answered both questions at the same time. So I looked at the total momentum of the two-car system before the collision, and you can consider each object separately. So the M1 V1 produces a momentum of 551,000 kilograms times meters per second. And since the loaded up car has a velocity of 0, the whole momentum of the object is 0. So that means that the mass times the velocity of car 1 is the total momentum of the two-car system before the collision, and this is the value. So the 1.12 times 10 to the 5th times 4.92, is that the number? 4.92, yes, that's it, produces this value. After the collision, the two carts are stuck together, so these two railroad cars are stuck together now, so you can add their masses together. So this is a larger value. It's 4.4 or something. It's listed up here in green. So in this example, 4.48 times 10 to the 5th times 1.23 produces a final momentum of 5.51 times 10 to the 5th kilograms times meters per second. So you can see that the momentum before the collision is equal to the momentum after. So in this case, the momentum is conserved. This is the idea that we were discussing above. The acceleration is directly proportional to the net force, so that if you have an object that has a larger mass, it will have a smaller acceleration. And acceleration, remember, is literally defined as delta V over delta T. So in this case, the question asks you to analyze energy to see if energy is conserved. And so in this example, the only energy that exists in the system is the energy of cart 1. So your kinetic energy of cart 1 is 1/2 mv squared. It produces a kinetic energy value of 1.4 million joules. After they stick together, you have this new mass and you have this new velocity. And if you calculate the kinetic energy of these two carts together, it's way less than what you started with. So in this example, you can see for inelastic collisions, kinetic energy is not conserved. It's transferred into other forms, whether it goes into like changing, like deforming the matter, or if it's lost due to work, or there are lots of other ways it can be not transferred. But in this example, the motion or the mechanical energy of cart 1 and cart 2 are not conserved after the collision. We skipped this question in class, but if you would like to review it, this is how it's done. So this is another example asking for something that sticks together. So all of the momentum at the beginning, so both objects at the beginning added together, need to equal the momentum at the end. So the total momentum at the beginning needs to equal the total momentum at the end. That's the idea of conservation of momentum. Now this number, when you multiply m times v, is a positive 12.1224 m. That value needs to be included. And the momentum of object 2 is to the left. So this one is moving south. So it's important to include the negative symbol. So in this case, it has a momentum of negative 6.12. And so the total is the sum of these two separate objects' momentums. So this 12.24 plus a negative 6.12 produces a total momentum of the two cars to be 6.12 m. That's a part of it. And then the units. And at the end, the momentum is the sum of the two masses because they are stuck together now. And both objects are traveling together. They're stuck together, so they have the same final velocity. So we basically just like factor out this v. So m1 plus m2 is 5m times v. So we take the total momentum at the beginning and divide it by the mass of the momentums at the end to produce a final velocity of 1.22 meters per second. So this little m1, v1, m2, v2, v1, v2 prime chart can be really helpful if the problem asks you to solve for a final velocity. So that's it. Good luck studying for a test or quiz. I hope you do really well.